Welcome back everyone. In this lecture I am going to do some computation of character tables for some smaller groups. So, let us actually begin with the group of Quaternions. So, let us actually recall what it is. The Quaternion group so we denote it by Q8. So, what is Q8? As a set, it consisting of following elements plus or minus 1, plus or minus I, plus or minus j and plus or minus k. So, basically they are the units in the 4-dimensional algebra called Quaternions. So, I am going to just tell you like how this group is defined. So, basically we need to actually write down the multiplication table. So, I am going to write down the minimal set of relations. So, you can recover everything from using this relation. So, I square, j square, k square, all of them are minus 1, and when you multiply I j k, that is also going to be minus 1. So, using this you can recover all possible multiplication of these elements. This is basically non-abelian group. So, you can see that non-abelian group of order 8. So, the order is 8, and if we actually take I j, so that is going to be exactly k, and then we can also write down other possible products. So, maybe I will leave it as exercise. So, one way to remember the multiplication, so we can actually write I j k in clockwise direction, and then so we just read it off. So, whenever you take the product I j, that is going to give us k. So, that is how we remember. So, you can see that I j must be k, and then j k must be I, and then k I must be j. Similarly, you can also compute the other ways. So, j I is going to be minus k. So, from this it is clear that this group is non-abelian. So, this is non-abelian group, and similarly k j is going to be minus I, and then I k is going to be minus j. So, basically if you go anti-clockwise, so I k is going to give us minus j. So, that is how you can actually get all possible products. So, now if we actually think about it, one can prove that the center of this Quaternions that is going to be plus or minus 1. So, all these basic facts that I am going to recall from group theory, and I am going to leave it to you to check. The center of the Quaternions, so this is the center. So, this is exactly plus or minus 1, and the center is same as the commutator subgroup. So, if we take this commutator subgroup of this Q8, that is also going to be plus or minus 1, and in particularly, so the quotient is going to give us all possible degree 1 representation of Q8. So, if you think about it, if you go modulo the center, so then what we get is actually Klein 4 group. So, this is going to be isomorphic to G modulo 2 z cross G modulo 2 z. In particularly, so the I bar, which is an element in the image of I inside the quotient, so that will be mapped to this 1 comma 0, and J bar, so that is going to be mapped to 0 comma 1. So, this is the isomorphism that is given here. So, this is easy to see because so when you are actually multiplying I and j, so you can see that I and j gives us k, similarly j I gives us minus k. So, in particularly when you are going to the quotient, so you can see that this k is same as minus k. So, that is why I bar and j bar commutes in the quotient, and both of them have degree 2. So, and since this has order 4, it must be isomorphic to G modulo 2 z cross G modulo 2 z. Okay, so now we have this quotient which actually of order 4. So, that is going to give us 4 degree 1 representations of Q8. So, now let us write down all possible conjugacy classes. So, again I will leave it as exercise. So, the conjugacy classes are follows. So, first you have just the identity, and then second you have the negative of this 1, and plus or minus I, they will be in same conjugacy class. Similarly, plus or minus j, that will be same conjugacy class, and plus or minus k also will be in same conjugacy class. So, let me do one example. I will leave it to you to check this. So, if we take for example, the conjugate of j by I, then the inverse of I is minus I. So, I j minus I is going to be exactly k times minus I, which is exactly minus k I, which is exactly minus j. So, you can see that j and minus j, they are conjugate. Similarly, you can prove all these things, and since this is the complete list, so these are the conjugacy classes of Q8. So, now we have 5 number of conjugacy classes. This is the number of conjugacy classes, and we already have 4 degree 1 representations. So, that tells us that the cardinality of Q8 is exactly 4 plus d phi square, because there are 5 number of irreducible representations. So, now the order is 8. So, from this you can conclude that d phi square is exactly 4. So, that means d phi should be 2. So, there is a 2 dimensional irreducible representation of this Q8. Okay. So, I am not going to tell you what is that representation, maybe you can think about how to construct it, but I am going to actually just write down the character table. So, what we are going to do, we are going to use all the machinery that we have actually developed so far. So, we recall that degree 1 representation can be obtained by lifting all degree 1 representation of the quotient. So, which is isomorphic to G modulo 2z cross G modulo 2z. So, now we already seen that I bar actually map to 1 comma 0 and then j bar map to 0 comma 1. So, if we use this, then we can actually write down the table. So, let me just write down. So, let us list all possible conjugacy classes. So, here is chi 1, chi 2, chi 3, chi 4, chi 5, and then on the other hand we have all possible conjugacy classes here, 1, minus 1, plus or minus I, plus or minus j, plus or minus k. So, now if we actually look at the number of elements in the conjugacy class, so this is exactly 1, this is again 1, this is 2, this is 2, this is 2. So, now we are going to use all this information. So, since this one is trivial, so we can see that the values of the chi 1 of these conjugacy classes, that is all going to be 1 1 1. So, this is all going to be 1 1 1. So, now let us actually fill these chi 2 and chi 4. So, these are all one dimensional representations. So, that is actually comes from the lift of this. So, we take one dimensional representation of this and then lift it to Q8. So, from that we are going to get all these things. Now, you can see that plus or minus 1. So, this is going to be in the kernel of all the representations, row 2, row 3, row 4. So, that means, so all these entry is going to be 1 1 1 1. So, now we need to actually pick what to assign for this I bar and j bar. So, you can see that any homomorphism from this G modulo 2Z cross G modulo 2Z to C cross, that will be determined by the values on this I bar and J bar. So, that is what going to give us, because it is all one dimensional, the exact values will be given here. So, we can actually make choices. So, for example, we can take I bar actually is sent to -1 and then j bar sent to 1. So, that is going to give us one representation. Similarly, we can also choose I bar sends to 1 and j bar sends to -1 and so on. So, if we actually take those values, then you can see that. So, this is going to be -1, this is going to be +1, these are all the values that I am assigning to I bar and j bar, and I bar j bar is nothing but k bar in the quotient. So, that means the product of this is going to be here -1. Similarly, here 1 -1 and then the product will be -1 here, and here -1 it can take, because we are looking for order 2 elements. So, we can assign I bar 1 and j bar 1. So, let us say this is row 2 and this is actually row 4, and that is going to give us 1 here. So, now how to fill the last row? So, here it is going to be the degree of the representation. So, that means we can already did the computation, we already seen that the degree is 2. So, there is one 2 dimensional irreducible representation. So, that is going to be filled here. So, the degree is 2. So, we will actually get 2 here. So, now the remaining entry, let us call it A, B, C, D. So, what we can use? We can use orthogonality relations to conclude the values of A, B, C, D. So, let us actually look at the orthogonality relations. So, let us actually compute what is chi 1, chi phi, and then see what happens. So, chi 1 is this. So, this is exactly chi 1 and then this is chi phi. So, we are going to say, so recall, so what is the inner product? So, inner product chi dash is nothing but 1 divided by the cardinality of G summation chi of G chi dash of G bar, G runs over G. Since chi dash both are class functions, so we can rewrite this as follows: 1 divided by the cardinality of G summation I range from 1 to S, the cardinality of C I, because chi G will be same throughout all elements of C I. So, then you get chi of G I, let us say G I is the representative of C I, and then chi dash of G I bar. So, this is exactly the inner product. So, that means this chi 1 inner product chi phi is exactly equal to, so the first conjugacy class you can see that this is corresponding to 1 and the number of elements there is 1. So, it is exactly 1 times 1 times 2. Similarly, you can see that the second conjugacy class has cardinality 1 and the value is 1 here and then value is A. So, you get exactly 1 times 1 times A, 1 times 1 times A. Similarly, you can see that the third one 2 times 1 times B. So, 2 times 1 times B, and if you write all of them you get 2C and 2D, which is supposed to be 0. Similarly, when you compute chi 2 chi phi, you can see that this is again going to give us 2 plus A, and then let us look at the third entry. So, this one, so the number of elements in the conjugacy class is 2 and the value here is -1 and then here is B. So, it is going to be exactly minus 2B, and similarly you can see the third one is the third one is again this is 2 and then this is 1 and C. So, again this is 2C and the fourth one is 2 and minus 1 and D. So, the product of those. So, minus 2D and this is supposed to be equal to 0. So, let me write down all other equations. So, chi 3 chi 5. So, this is exactly 2 plus A plus 2B and minus 2C minus 2D, minus 2C minus 2D which is 0. Similarly, chi 4 chi 5 2 plus, so now the value okay, this is also A and then so the number of conjugacies classes is 2 and the value is minus 1 and then B again similarly plus 2 minus 1 C plus 2 1 and D which is equal to 0. So, this is exactly 2 plus A minus 2B minus 2C plus 2D equal to 0. So, we got 4 equations. So, this is equation 1 and this is 2 and this is 3 and then this is 4. So, 4 equations are there and 4 unknowns are there. So, if you solve this linear system, so you can actually prove that you get exactly A equal to minus 2, B equal to 0, C equal to 0 and D equal to 0. So, this is what determines actually the values of A, B, C, D. So, now we can actually fill it here. So, this is exactly equal to minus 2 and this is 0 and this is 0 and this is 0. And now you can see that we have computed the character table of Q8 using the results that we have proved so far. So, similarly one can actually compute the character table of a dihedral group which acts on this let us say foregone, that is a square. So, people are using actually 2 different notation. So, let me just use D2n to denote the dihedral group which acts on the n-gon. So, this is the symmetric group on n-gon. So, I guess earlier I was actually mentioning this as D4. Sometimes people use Dn, but let me just stick with D2n. So, the 2n corresponds to the number of elements in the group. So, the order of D2n is exactly 2n. So, let me do this example where we have actually n equal to 4 which corresponds to the square. So, then it is not very hard to prove that this D8 indeed generated by 2 important elements of this group. One is the rotation by 90 degree and another one is reflection about let us say y axis. So, let me just draw this picture. So, we have this rotation. So, the rotation is about 90 degree rotation. So, that is your R, and what is S? S is, so we take this and then we reflect with respect to the y axis. So, just reflection with respect to y axis. So, that is my S. So, now it is a simple exercise to do D8 is generated by this R and S with the following relations. R4 is identity and S square is identity. Whenever you take the conjugate of R with respect to S, then you get the inverse of R, which is R cube. So, this gives us presentation of this dihedral group D8. So, now using this one can conclude the following. So, again I will leave it as exercise. The center of this the center or the derived the commutator subgroup of D8. So, that is given by this group which has order 2 are generated by R square, and then when you go modulo this commutator. So, you can actually see that this is indeed isomorphic to Z modulo 2 Z cross Z modulo 2 Z. So, indeed we can see that there is some similarity between the groups Q8 and D8. So, what happened? So, again it is not very difficult to prove that Q8 is not isomorphic to D8. But what is the similarity that we have? The commutator subgroups of these both groups Q8 and D8, both of them are isomorphic to Z modulo 2 Z, and when we go modulo the commutator, we are getting the Klein 4 group. So, basically, so both of them are extensions of this Z modulo 2 Z by this Z modulo 2 Z cross Z modulo 2 Z. But they are two non-trivial extensions, both are non-abelian extensions, they are not isomorphic extensions. But since they are extensions of these two groups, and since the commutator subgroups are matching means they are isomorphic. So, because of that we are actually going to get and the quotients are also isomorphic. So, because of that we are going to get a same character table as Q8. So, what are all the conjugacy classes? So, the conjugacy classes are going to be, again there are 5 conjugacy classes, identity and one element R square, and then these 2 elements R and R cube, and fourth one is going to be S R square S, and fifth one is going to be R S R cube S. So, these are all the 5 conjugacy classes of D8. So, that means number of irreducible representations, so that is going to be exactly 5. So, we can again go back to that equation, we will get D1 square plus D2 square plus D3 square plus D4 square plus D5 square equal to 8. Now, since the quotient of the commutator is isomorphic to G modulo 2 Z cross G modulo 2 Z. So, we have 4 one-dimensional representations. So, that implies that these are all 1 1 1. So, 8 equal to 4 plus D5 square. So, that would imply that D5 is exactly 2. So, we have 4 one-dimensional representation and 1 2-dimensional representation as before. So, then if you write it in the table, you can see that we are going to get exactly the same table. So, you have chi 1, you have chi 2, chi 3, chi 4 and chi 5, and then you have these conjugacy classes here 1 and R square R cube. So, let me write only the representative R, here S and then here R S. So, the number of elements in the conjugacy class, this is going to be 1, this is going to be 1, this is going to be 2, 2 and 2. So, it is very similar to Q8. So, now since as before we have D8 to the quotient D8 modulo the commutator D8 cross D8 comma D8, which is exactly isomorphic to G modulo 2Z cross G modulo 2Z. So, we can get 4 one-dimensional representation here and then we can lift it to D8. So, you can already see that the R bar will be mapped to 1 comma 0 and then S bar will be mapped to 0 comma 1. So, because of that you can again fill it the same way that we did it before. So, you can see that we will be getting exactly the same thing. So, you get 1 1 1 1 corresponding to the trivial, and then because these are in the kernel, these 4 one-dimensionals, we have to have 1 1 1 for this 1 and R squares. and for R, so we can actually make a choice either -1 or +1. So, this is -1, let us say 1, then you get -1 here, and then 1 -1 and -1, -1 -1 and +1 here. Similarly, the dimension of the representation is 2. So, then you get A, B, C, D satisfying the same set of relations that we had before, orthogonality relations. So, that will tell us we will be getting exactly -2, 0, 0 and 0 here. So, that means the character table of D8 and Q8 they are same, but the groups are not isomorphic. But of course, when I say the character tables are same up to the row permutations, that is what we have done. Again, up to the column permutation they are same. So, we arranged so that they look exactly the same, but even the character table up to row permutation or column permutation, if they are same, that does not mean that the groups that we started with need to be isomorphic. So, they do not need to be isomorphic. That is what this calculation actually tells us. So, we can use similar actually ideas in order to compute the character table of A4. So, which is even permutations in S4. So, maybe I will just outline and I will leave it to you to check. So, what is A4? So, A4 is those elements in S4 such that the sign of sigma is 1, even permutation. Then it is not very hard to see that the commutator of this A4, it is given by the Klein 4 group. So, which is given by identity and product of two transpositions, disjoint transpositions. So, identity and 1 2 3 4 and 1 3 2 4 and 1 4 2 3. So, this is the commutator group. So, in particularly if you go modulo the commutator, so then the cardinality of this is going to be 3, because the cardinality of A4 is 12, which is 4 factorial divided by 2. So, now this is actually a Klein 4 group, that means it is isomorphic to Z modulo 2Z cross Z modulo 2Z. So, that means the quotient has order 3. So, it must be cyclic group. So, A4 modulo the commutator is isomorphic to Z modulo 3Z. So, now if you actually think about it, the conjugacy classes, there are actually 4 conjugacy classes. So, let me just write down the representatives. So, here is the table. So, you have conjugacy class corresponding to the identity and the conjugacy class corresponding to this disjoint transpositions, and conjugacy class corresponding to this cycle 1 2 3, and its inverse is not going to be conjugate to 1 2 3. So, that is going to actually lie in the different cycle, different conjugacy class. So, then the sizes of these conjugacy classes, this is going to be 1 and this is going to be 3, because all of these product of disjoint transposition, they are conjugate in F4, and there are 4 actually 3 cycles that are conjugate to 1 2 3. Again there are 4 cycles which are conjugate to 1 3 2. So, maybe just list all of them. So, 1 2 3 actually conjugate to 1 3 4 and 1 4 2 and 2 4 3. So, these form one conjugacy class corresponding to 1 2 3. So, we have this, and then here we have again chi 1, chi 2, chi 3, chi 4. So, now if we go back to the argument that we gave, so we will be filling 1 1 1 in the first row, and then since 1 and 1 2 3 4 they are in the kernels. So, we will be filling 1 1 1 1 1 here. Since the quotient is Z modulo 3Z, there is going to be 3 one dimensional representations. So, and they corresponds to these 3. So, now now we have to see like where the generator actually goes. So, 1 2 3 bar is going to be the generator. So, we can choose omega for that. So, then 132 is going to be omega square. Similarly, if we choose omega square for 123, then 132 will get the value omega. So, now the degree of this representation, that you can see that it is 3, because there is 3 plus d 4 square is supposed to be 12, which implies that d 3 square is 9, that would imply that d 3 is 3. So, now we have to fill what is ABC, and using the orthogonality relations one can prove. So, maybe let me leave it as check that using orthogonality relations A is -1 and B is 0 and C is 0. So, this is going to give us the character table of A4. So, these groups, like you can see that Q8, D8, A4 and so on, they actually kind of fits into this important framework, where the commutator group is big enough and the quotient is indeed abelian, and this is big enough quotient. So, in particularly we are able to actually get all possible one dimensional representations, and since the number of irreducible representations, they are actually very small, we are able to actually get it very explicitly what is the character table. And when we go to symmetric group on 4 letters and so on, we need some more preparations, maybe like later I will be able to tell about it once I introduce a tensor product and so on. Okay, I will stop here, and we will continue with the Burnside's theorem in the next class. Thank you.